My name is Paparo, and what I will be showing you today is the synthesis of one of the main starting materials that we use in our lab in order to prepare beryllium complexes. This compound, the beryllium dibromide etherate, has been known for quite some while, since the 50s. It was a Russian group that synthesized it first. What you need to produce this compound is simply you take beryllium metal. We will take it in form of beryllium powder. You take some not pre-dried bromine, just bromine straight from the bottle. Combine it in diethyl ether. Allow it to reflux for quite some while until it forms this nice, beautiful off-white precipitate, which is the beryllium dibromide dietherate. And then you isolate it through standard organometallic lab techniques. So let's get it started. What we have prepared for you guys is, on the one hand, here's some beryllium powder in a Schlenk flask, which is sufficiently large. We also prepared a reflux condenser, which is in order to keep the diethyl ether inside. Otherwise, it will boil off quite immediately. And here another flask straight out of the oven. It's not so hot anymore. It's set under dynamic vacuum right now, in which we will put the bromine and some dried diethyl ether, and then cannula transfer it into the reaction vessel later on. So we'll wait a little bit until this one cooled down. We will do one more cycle, then introduce the bromine here and add the ether.
Just beware, I need to wear a mask. It has a particulate filter and also a chemical vapor filter. This is really important always when you work with beryllium to wear a mask because of the potential high toxicity of beryllium. Also, we will be working with bromine today, and as a man, you should never let bromine near you in any way. I will take bromine and dilute it with diethyl ether before adding it to the beryllium powder, which is suspended in diethyl ether as well. So this flask has been evacuated and dried, so there is no residual water in it. I will refill it with nitrogen right now. Okay, regulate the stream a little bit. Okay, it's going through. That's very good. So what I will do is also refill the beryllium flask and the reflux condenser with nitrogen. Okay, now what we need to do is, even though we are taking wet bromine, it's always good to flush your needle and your syringe before use. Just standard practice, so you don't do mistakes in other instances where it's important to keep everything dry. So now let's carefully take in the bromine. It's 5.2 milliliters, which I will need to react with 930 milligrams of beryllium. Okay, I will just leave the needle in the background so the bromine can evaporate. And I will introduce the ether next. I take away the needle so I don't lose too much of the bromine into the atmosphere of my fume hood. So let's put that to the side. So I need to put a septum on the beryllium vessel as well, because I will use the same cannula in order to introduce ether into both vessels. Good. So I keep my solvents always attached to a secondary shrink line. I attach to my main shrink line. We keep our solvents in these solvent bowls. They're from stills, where we dry them over sodium and sometimes also sodium-potassium alloys. After taking them down from the stills, we gas them in a stream of dinitrogen, and then they're ready for use, and we keep them in the fume mode. I have a clean septum that I only use for solvents. That's very important. You don't want to contaminate your solvents with anything else. Let's just clean the headspace with a little bit of nitrogen stream. Okay, that should be fine. So now I will get a metal cannula and introduce the ether into both flasks. We keep our cannula at 120 degrees overnight, so they're drying up, so we don't get any water through the cannula into our reactions. What I will do is stick the hot cannula into the vessel of the solvent and first flush it with a little bit of solvent, because you never know what your colleagues or you yourself did the evening before, so you want to make sure it's clean. Okay, great. It's colorless. It seems to be clean enough. So what I will do is now just stick it in here. Allow for some pressure equilibration and close the stream on the side of the on the vessel where I want to introduce the solvent into. Upsala. And it's a little bit exothermic, but don't worry. If you want, you can cool it, but it's fine. So you might lose a little bit of the bromine, but that's not too bad. Okay, great. So what I will do is just go to the other side and add some ether as well. There is no harm in adding a lot of ether, because it's a solvent that's easily removed, and it's better to have more ether than no ether at all at the end. Okay, wash off the beryllium powder nicely down from the walls and collect it on the bottom. For this amount of beryllium and bromine, I will use something like 80 milliliters of ether, and here approximately 40 to 50 milliliters of ether with the bromine, so we have sufficient solvent. We always keep some cardboard or something soft for the case if the flask just bumps. That happens sometimes, especially when you're just starting as a organometallic chemist. You might break your flask and then cause some major spillage. So you want to avoid that. And this cardboard saves you from these small annoying bumps. Open up the gas flow and close the ether. We don't need it anymore. Okay. Close the flask. Put it to the back so it's not in your way. Great. And now just for a moment I will close the vessel in order to be able to prepare the cold bath. Okay. Please see, I'm not closing this one in order to avoid building up of overpressure. If there is overpressure, it will go into my nitrogen line, but it will go out of the bottle, so that should be fine. Good. Since I performed a couple of operations and stained my gloves, as always, I need to replace those gloves on a regular basis in order to avoid poisoning myself. And here I can close it because this one is cool and it doesn't involve any heat. Also see here, bromine is nicely covered. It won't evaporate that easily into the stream. What we need to do next is attach the reflux condenser on top of the reaction vessel and then introduce the bromine on top of the reflux condenser. So it will run down the reflux condenser into the reaction vessel while we are cooling down the reflux condenser. Okay, open this one. Just grease it. Always make sure to have it sufficiently greased, but not to the very bottom, because you don't want to contaminate your reaction with grease. And ether dissolves grease very easily. Clamp it. And then we remove this part on top and put a septum there. So what we need now is a good cooling. And what we will take for starters is a minus 80 degree cold bath, which we will produce with ethanol and dry ice, which is basically solid carbon dioxide. Now we will lift that carefully, just a little bit, so we can put the cold bath below. Okay. We need to ensure that cooling, that steering is still taking place. We see the vortex, so everything is totally fine right now. Before we introduce the bromine through the reflux condenser to the reaction mixture, we need to make sure that we have a good cooling set on top. For that, we will use just cooling water from the tap, which we have right here. Sometimes the water flow can be a little bit strong, so it's always good to secure your hoses via clamps. Okay, attach it properly, strongly. Okay, double check if it's holding. Just introduce water slowly, carefully. It's dry. And it's dry, so there is no water leaking. Okay. Allow the stream to go out a little bit, so we don't trap any oxygen or moisture in the headspace of the septum. Okay. Now let's pre-cool it a little bit. You can see the bromine already starts to solidify. This is a good sign. Now we can mix it quite safely. As you can see, you form a nice orange suspension in the ether. I let the cannula be flushed by a nitrogen stream. Yeah. Before introducing it into the septum there. Okay. So you won't be able to see it because it will be on top in the fume hood, but I will stitch that into the septum here on top. Okay. Introduce the cannula as far down as possible. And dive this end here into the bromine. Of course, there is still no bromine coming over because we introduced nitrogen here, nitrogen there, so you have the same pressure on both sides. But I will regulate the stream and the stream flow by decreasing the pressure that I apply with the nitrogen stream on this side. And by that I can ensure that I don't add the bromine too fast. And by that I can also regulate the temperature of the reaction. We have to do it very carefully because if the reaction starts too quick, yeah, as you can see, it reacts viciously. So we have to be extremely careful and only add it very slowly. As you can see here. Yeah. Okay, slower. We will increase the flow a little bit so we ensure a reaction occurs and mixing of the reactants occurs quickly. Of course we lose some bromine, but that can't be avoided if we want to work safe. Everything is still cold here, so that's a good sign. That means we are still safe. As you can maybe see here, we have a constant stream of reactant running down. Yeah, I mix it here on this side a little bit so we don't only get the ether transfer but also the bromine. Yeah, you can see it boiling now a lot because it's reacting like hell. So good that we're cooling it. That will keep us safe and the reaction going. Okay, I will completely transfer all the bromine. Good, it's done. Good, and now we let it steering for a while until it's completely converted.
Yeah, welcome back, folks. As you might have seen in the time lapse, the reaction proceeded smoothly. It changed color from orange-yellow to almost colorless, as you can see. There is plenty of colorless or off-white precipitate here, which is the beryllium dibromide etherate. Of course, you can also see a little bit of grayish particulates. This is still some unreacted beryllium powder, but the workup that we will perform right now will make sure that we will get rid of all the beryllium that's remaining in there and that's unreacted. Beryllium dibromide etherate is partially soluble in diethyl ether, and if we added an excess of ether or we heated the whole story, we would be able to extract it with diethyl ether. However, it might crash out in the filtrate or in the filter cannula because ether evaporates very easily, and that might clog the filter cannula, and that will make the whole story very difficult. Because beryllium dibromide etherate behaves differently than the magnesium dihalide etherates, which are very insoluble in toluene, this one on the other side is very soluble in toluene, so we will just strip it dry and extract with toluene and then keep it for crystallization. So what I prepared a little bit earlier is a flame-dried vessel to collect all the ether, because there's plenty of ether. Of course, we don't want to pull it into our solvent trap of the vacuum pump, because you don't want to destroy your vacuum pump. They're pretty expensive. So we make sure it's in the counter stream. Yeah, and this one is open, so now we can combine them. Good, regulate the stream a little bit. Open carefully. Okay. Yeah, you can also hear it. There is nitrogen escaping from the connector. Let's bring them a little bit closer. Okay. They're nicely connected, so now I can close this part here and also the part on top, because I want to pull some vacuum first before I open this one gently. So you will hear it, the vacuum pump will start sucking. Okay, this is quite a large volume, it'll take a while. And we will already insert the solvent trap into a dewar, which we will fill up with liquid nitrogen right now in order to collect the ether in there. So with this mercury manometer, we can check if the pressure is nice. Yeah, it's quite fine. It's not perfect, but you wouldn't expect that because the joints are not that perfect and are not being used very often for high vacuum work. So now we will close it and keep it under static vacuum. This vacuum is sufficient to transfer the solvent into the colder vessel right here. Now we will carefully open this one here, this valve, in order to start the evaporation of the reaction solvent. Okay, as you can see, it started evaporating and solvent condenses on this side here. Later on, when this starts to freeze and to become really cold, we will heat it gently with a hair dryer in order to speed up the process. I need to heat it a little bit, but on top, not on the bottom. If I heat it on the bottom, it will shoot up. It doesn't have to be a complete removal of ether because it won't harm too much, but in general it's good to keep everything simple, so try not to mix solvents too much when you crystallize. Also, what you can see here on top is that's the usual impurity that you get when you produce this compound. So through recrystallization from toluene we will get rid of this one, of course. Instead of static vacuum, I will pull dynamic vacuum in order to get rid of most of the ether. I will close this one first. pull good vacuum on the trap and then open this one back again. But what you can see here already is the product. Yeah, but it's still not clean. We will need to recrystallize it. But you can see there is already plenty of colorless solid. We stopped the evacuation and drying of the product, and we will reintroduce nitrogen into the vessel. Okay, so we'll disattach the connector to the solvent trap and put a septum on top, through which we will introduce the toluene now. Okay, put a needle on top. As I showed you earlier, make sure that your cannula is clean. So flush it with a little bit of solvent. Very good, everything is clean. And now we can introduce some solvent. Close it to have an overpressure on this side. Remove the cannula. Let's go. We will need quite a bit of toluene in order to dissolve all of this, because it's a lot of product. That's a little bit more than 100 milliliters, maybe something like 130 milliliters. That should be okay. So we remove cannula and let it steer for a while. What we will do next is filter this one into a fresh vessel where we can crystallize the product. Yeah, let's create some space. Do it this way around. And heat it up a little bit to see if we can dissolve everything. Okay, great. So when filtering, we will cease stirring in order not to destroy our filter. So we introduce the cannula in the counter stream. Let some of the headspace escape. Okay, the cannula is flushed nicely right now. We can introduce it into the next vessel. Introduce the cannula to equilibrate the pressures. Close it. And as you can hear, maybe, there is still gas flowing over and it escapes on this side. Even though this one is closed, gas is flowing out. And now, let's start the filtration. Okay. So, the product is dissolved in toluene. You can see it by the yellow color of the toluene solution. Most of the time later on when you perform reactions with beryllium dibromide etherate, the solution is colorless, but here it's very concentrated and there might be some residual bromine, so that's why there is some color. So what we will do today, and then we'll place the reaction vessel in the crystallization vessel into the fridge to get the nice crystals of our product, is finish the filtration, extract once more with some more toluene until there is no more color of the filtrate. Then we'll pull it dry a little bit under vacuum until incipient crystallization occurs, and then we'll close it up wrap it up with some paraffin and place it into the fridge at minus 30 degrees centigrade. Yeah, and I'll see you guys in 2 days. Okay, welcome back, guys. It took us 2 days to get the product to precipitate. So this here, the beryllium dibromide etherate. So what I actually did in the meanwhile, because the crystals didn't want to come out from toluene, that happens sometimes. It was oversaturated. It was a very dark, tarry solution which couldn't be pumped dry. So I just added some diethyl ether, shook the whole story, sonicated for a while until incipient crystallization occurred, and then I put it back into the fridge at minus 30 degrees centigrade. And as you can see, we got plenty of microcrystalline beryllium dibromide etherate, which we will now isolate through filtration into this prepared and flame-dried flask. Also, just to show you, we use ice in order to cool it down, so we don't have any beryllium dibromide etherate dissolved in the solution, and we can increase our yield. So let's backfill nitrogen into the vessel and connect both of them with a cannula. Okay. And like always, we need to let some of the headspace escape, so we make sure there is no oxygen or water trapped. Okay, now let's connect both of them. Close this side in order to have an overpressure on this side, and push the solvent to the other side. The impurity is colored slightly brown, and we'll give it another wash with diethyl ether to make sure that we got rid of the impurities. We will lose a little bit of product, but we will still have plenty of product. Yeah, so last time after extracting the product with toluene, there was some unreacted beryllium powder in the vessel left, and we isolated it, and after thorough drying under vacuum, we will employ it to produce some beryllium diiodide dietherate maybe. So of course this will make our yield be a little bit lower than anticipated, but that's totally fine since we recovered the beryllium powder, which is the most expensive part in the whole story. Okay. So you can see it here, this colored powdery material. That's the beryllium dibromide etherate. It's not entirely colorless, and it will never become entirely colorless. It will be actually a little bit grayish. Let's give it just another wash now. Okay, as always, we give the cannula a short wash. Okay, everything good. Okay. We will use something like 30 to 40 mils of ether, of cold ether, to give it a last wash. Okay, that should be fine. Okay, now let's shake it a little bit. As you can see, the solids are now grayish, as I predicted, and the filtrate solution is not too colored anymore. can see, it's almost colorless. It's good. Hey boss. Let's close them up. Okay, this is now the product. We will pull some vacuum to dry it and get rid of all the uncoordinated ether. Just pull gently in order not, otherwise it might bump. We leave this one for drying for approximately 2 hours to make sure that it's completely dry, and then we'll bring it into the glove box, isolate it, weigh it out, take a proton NMR and a beryllium NMR spectrum in deuterated benzene, and then we are good to go. We can use it. Thanks for watching, guys.